Today we're going to start section 3.2 over things called sequences and strings. And these are both common ideas anytime you're doing something on a computer with programming. And first we're going to talk about an intuitive definition for what a sequence is, and then we're going to talk about the more rigorous mathematical definition. But if you have this intuitive notion in mind, you should be safe, I think, on most of your homework. A sequence is actually a very simple idea. It's simply an ordered collection or an ordered list. So it's something like a set. Remember, a set is just a collection of objects, but now we don't want to think about it as just a conglomeration of things. We want to think about it having some sort of order. So something like an ordered pair or something like that. And there's all sorts of examples that we could talk about for lists. A very simple kind of list would just be the counting numbers, 1, 2, 3, 4, 5. And the dots here mean that this could continue off to infinity. So it's possible for a list to be, it's possible for a sequence to be infinitely long. Let's see, so there's a question about whether you have to state that a sequence is infinite, and it kind of depends on context. If you're doing something on paper like this, the dots will always mean that it just continues, the pattern just continues. So you don't have to specify what the dots mean. That's what they're used for. So sequences could or can continue forever, or could be infinite, I think is what I meant to say here. If you have a finite sequence, you'll include a stopping point. This particular sequence isn't very interesting. It's just, the list of counting numbers. You can have other kinds of things, like maybe the even numbers, 2, 4, 6, 8, 10, and so on. These sequences are both infinite. They continue forever. But as I said, a sequence is any ordered collection, so it could also be finite, like the letters in a word. Here's one example. So here I've just taken the letters in the word discrete and listed them out. So this is a finite sequence. And one thing that you should notice that distinguishes something like a sequence. Okay, and I'll answer that question in just a second. There's something special that distinguishes a sequence from the set idea. And that's that you can have repetitions in a sequence, because now the order matters. So elements in a sequence can repeat. Remember, in a set, you can only have one of a single object. Like a set can only have one copy of the number 1 in it. But in a sequence, you could have 1 any number of times. And William is asking if there's a special notation for sequences. And there is a little bit of notation that I want to talk about. I guess maybe I'll write my last example and then I'll show you what that is. Here's one more sequence of digits. Maybe someone can tell me what this sequence is. I'll just keep on writing until until I get tired of doing it. Okay. Yeah, so these are the digits of pi. Good. And this is also an infinite sequence. And you can see that there's repeated numbers in it. So 1 repeats, 5 repeats. Let's see. 5 repeats actually 3 times here. 9 is in a couple places. Yeah. Okay, good. So to answer the question about special notation, I was planning on putting that on the next page, but this is as good a spot as any, I suppose. So if you don't want to write out elements of a sequence, there is a shorthand notation. Let's see. So this first one, which was just the list of numbers, I could write like this. So I use curly braces and then a formula for the item in my sequence, the element in my sequence. And then I have this notation that tells me to go from 1 to infinity. So this lower number is your starting point. Things are getting a little crowded here, unfortunately. And then the upper number, in this case, infinity, is your stopping point. And if you see an infinity up here, that means that you don't actually stop. You just keep on going forever. So this would be how you might write an infinite sequence using just a little bit of notation. And we'll see that a few more times to get some practice with it. Any other questions right now? No? Okay. So like I said, this was the intuitive definition. A sequence is just an ordered collection or a list. Let's get to the more concrete mathematical definition. So a sequence is actually a kind of function. It's a function whose domain, which I'll call D, is a subset of the integer. So returning to this first sequence of numbers, since this is a very simple one, we can think of it as a function from the positive integers to the positive integers. That doesn't actually do anything. if you plug in a number, then it just spits back out the same number. So this corresponds to the ordering. So if you plug in a number in order, or an ordered number, let me just put an arrow here that reminds you that the integers have an order, then things are spit out in that order. Okay, but this notation is a little clunky. We don't actually want to write functions all the time. So usually instead of that notation, we'll use something like this. So we'll use S to represent the sequence, and then we'll have a subscript, a little tiny n written below S, instead of writing it this way, like a function. So this just is a more compact way of writing the elements in a sequence. And this term n in my sequence is what we call the index. So indexing might be a familiar idea if you've done much programming, where you have to use lists or loops. And that idea gets brought in here in sequences. It tells you where you are in the sequence, the nth term. And if D is finite, remember D is the domain of the sequence, then you're actually looking at a finite sequence because you can only plug in a finite number of things. And if D is infinite, if your domain is infinite, then your sequence is infinite, meaning it just keeps on going forever. So before we go to the next page, are there any questions over notation or the basic idea of a sequence? Okay, so let's work through a few more examples and some special types of sequences that you'll see fairly often. The first kind of sequence that I want to talk about is an increasing sequence. And here's the technical definition of an increasing sequence. And a sequence S is increasing if for all and j in the domain of your sequence, if I is less than j, meaning I comes before j in the sequence, then the value of the function at I, the value of the sequence at I, is less than the value at j. Okay, so like I said, this is a bit technical. What does this mean in practice? Let me just write an example. So this sequence is increasing because if I compare two things in my sequence, like say I pick one here and then I compare it to something later on in the sequence, the one later on is always going to be larger. So this is like index 2, and this one is index 6. So S of 2 is less than S of 6. Let's think about this just for a second. If I wanted to write a formula for Sn, what would it be? So what's the nth term in my sequence? N squared, good. So this is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. So the next term in the sequence would, of course, be 49, and then 64, and so on and so forth. So if I didn't want to write out this sequence by hand like this, I could just use that notation. I could write it this way. I could say Sn from n equals 1 to infinity, since I already have a formula for Sn written over here. Or I could just write out that formula. I could just say n squared instead of Sn, where n is equal to 1 up to infinity. Remember, this is the notation that we might use. Okay, any questions over that little example there? No? Okay. So the next kind of sequence is a decreasing sequence. And this is, of course, the opposite. So a sequence S is decreasing if for all I and j in the domain, if I comes before j, then S of I is greater than Sj. So the element earlier in the sequence is greater than the element later in the sequence. That's what that's saying. And here's another way to write a sequence. I could just say something like AI equals 1 over I for I greater than or equal to 1. So this is another way that you might see a sequence written out without writing out elements. So if we wanted to translate this into a written out sequence, we would have to start plugging in values for the index. So the first element in the sequence would be where I is equal to 1. So that would be 1. 1 over 1 is 1. What's the second element in the sequence? Anyone want to say what the next element would be? No volunteers? Oh, okay, there we go. Yeah, so you just go to the next number, 2, and 1 over 2, there's nothing to simplify really, it's just 1/2. And then the next element, you go up to 3. 1 over 3 would be the next one. And then that would just continue. So 1 over 4, 1 over 5, 1 over 6, and so on. So this is a decreasing sequence because the values of our fractions are decreasing as we go further along. We're dividing by bigger numbers, so our fraction is getting smaller. Right, William, this does look very much like the pseudocode for a loop. I think it's maybe written a little bit backwards, but yes. So a lot of the ideas from programming and pseudocode are rooted back in mathematical concepts, because the earliest computer programmers, actually, the people who developed computers, were all mathematicians. If you look at the history, mathematicians interested in doing big problems that they couldn't do by hand, basically, or engineers or something like that. Right. Yeah. Yeah, if you look at the nuts and bolts of a CPU or something, really all it's doing is adding and subtracting and multiplying and dividing. So programming is trying to convince something that can only manipulate numbers to do more interesting things for us. Okay. So the next idea for a sequence is very close to the last few, but there's a subtle difference. A sequence is non-increasing. So that means it doesn't increase. If for all j in the domain, if I is less than j, then the next, or the later item in the sequence, j, must be less than or equal to the one before it. So now it's possible for it to actually be equal. A little silly example for this one would be this sequence. Of ones just repeating forever. So this one's non-increasing, it never goes up. Maybe that's a good way of thinking about non-increasing. If you want a little bit of intuition. So this sequence of ones never goes up any, but it also never goes down. But it is still non-increasing. Okay, and then there's also the idea of non-decreasing. Which is really closely related. This one tells us that the earlier elements should be less than or equal to the elements later on in the sequence. So the precise definition is a sequence S is non-decreasing if for all j in the domain of the sequence S, if I is less than j, then Sj is less than or equal to, Si is less than or equal to Sj. So this sequence here, another silly little sequence that doesn't really mean anything, is non-decreasing, because if you compare an element over here to an earlier element, it's at least as big as the one before it. So even though some of the numbers repeat, it's still greater than or equal to the preceding element. So that's still fine. And this particular sequence, I stopped writing. I didn't put any dots, just to show that it's actually a finite sequence. But you might see the pattern. It could repeat forever if we wanted it to. Okay, any questions before we flip the page? Okay, so these sequences that we've been talking about have all been kind of just given by a formula, or I've just written them down. Sometimes sequences are defined a bit differently. Uh, for example, this is a famous one, the Fibonacci numbers. You might be familiar with them. And they work something like this. The first two elements of the sequence are 0 and 1. And if you want to go to the next element, what you would do is use this formula. So Sn is equal to the sum of the previous two, Sn minus 1 plus Sn minus 2 for n greater than or equal to 3. Okay, so let's see if we can write down some of the elements in the sequence. 0 and 1 are the first two. What's the next number? Anyone know the next number in the sequence? So you would use the formula. S3 is equal to S2 plus S1. So it's just the sum of the previous two. 1, right. What's the next number after 1? 2. Good, 1 plus 1 is 2. And maybe just keep on going. 3, good. Let's just go up to until we get bored or something. Yeah, 5, 2 plus 3. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. 13 plus 21 is 34. 21 plus 34 is 55. 34 plus 55 is 89. You get the idea. So if we wanted to keep on going, we would just add these two numbers to get the next one. So this formula here is what we call a recursive formula. So recursion means you refer back to something earlier in the sequence to get the next one. I think this is also a common little coding project when you're learning a language, a computer coding language. You can try to figure out how to get your code to compute the Fibonacci numbers using a recursion. Any questions over that idea? Okay, so one important and kind of limiting quality of a computer is that a computer can only handle a finite amount of things, right? You only have a finite amount of space, of memory space. You only have a finite amount of time that your computer can actually run. So these infinite sequences, like the Fibonacci numbers and the ones before it, you can't actually do these in computer science. You can't actually use them in an actual computer. Maybe in theory, you could think about what might happen with an infinite sequence, but you couldn't actually do it. So in practice, what you have to use is something else. Actually, we're not quite there yet. Never mind. That's on the next page. We're talking about subsequences right now. We'll get to that other idea on the next page. So let S be a sequence, a subsequence. I got a little ahead of myself. Okay, a subsequence is what you probably think it is, just based off of its name. It's a piece of another sequence. And more technically, it's a sequence obtained by choosing terms from a sequence, which we called S, in the same order that they appeared in the original sequence. Let's do a little example of what a subsequence might look like. Let me define, oops, that should be a 2. Define a sequence using this little sequence notation. So the nth item in the sequence would be 2n minus 1. And we're starting at 1 and going on forever. So if we plug in 1, 2 times 1 minus 1 is equal to 1. Then if we plug in 2, 2 times 2 minus 1 is 3. If we plug in 3, 2 times 3 minus 1 is 5. So I think that's probably enough for you to see what this will be. These are the odd positive integers. So if we just write out a few more, it would look like this. Okay, and then let's look at this next sequence. Are sequences always integers? No, it's just that most of my examples are because they're convenient. But remember, one of our first sequences was just a sequence of letters, like the word discrete. So they could be real numbers or floating point numbers in computer terms, or they could be something completely different like letters. Does anyone recognize this sequence of numbers? Anyone see a pattern? 3 times n? Oh, multiply the number before by 3. Yeah, so if you wanted a recursive definition, that would definitely work. Like the Fibonacci numbers. You could say the starting number is 1, and then Sn is equal to 3 times the previous number. From 2 onwards. Good. And you might also recognize them as powers of 3. So 1 is 3 to the 0 power. 3 is 3 to the first power. 9 is 3 squared. 27, oops, 3 squared. 27 is 3 cubed. 81 is, oops. I have this bad habit of writing what I'm saying. 81 is 3 to the 4th power, and so on. And what you should notice that all of these are odd, and any power of an odd number is odd. So this is actually a subsequence of the odd positive integers. Okay, so you can see how we're picking only certain elements out. So we picked out 1, 3, 9, and 27 would be way off over here somewhere. So we're not picking things that are next to each other necessarily, but they are in the same order that they originally appeared in. And that's how subsequences work. Any questions? No? Okay. Let's see, so there's 5 minutes, and that feels like a good stopping point because I don't want to go on to the next idea. I think it'll take a little longer than 5 minutes. So if there aren't any questions, let's go ahead and just stop there for today.